going to be working the solutions for 2.2, the derivative as a function. I'm starting out here with number 2. I've already drawn a pretty good graph of what you can see here in the book, and we're asked for a bunch of stuff. A, we want f prime of 0, B, f prime of 1, C, f prime of 2. And let me just start with those. It says use the graph to estimate the value of each derivative, then sketch f prime. All right, so let's start out at 0, and we want to find the derivative at 0, which means we want to go to the x value of 0, which is here, and we want to look at the slope of the tangent line there. And well, it's pretty steep, okay? I'm going to make a real big guess here that the slope of this line is maybe 10. It's definitely not 1. 1 would be something like this, so it's steeper than that. I'll just go with 10. So this is what? Approximately 10. Then I go to an x value of 1, which is here. And let me just double check that on my graph. Actually 1, yeah, it's not very good here. 1 looks like it's this point up here, which if you look at the slope of the tangent line, it's flat, it's horizontal. So the slope of a horizontal line is 0. So this should be 0. And then the derivative at 2, here's 2. Okay, so if we go up to the function, something like that. Now the slope of the tangent line is negative. I'm going to say it's about -1. Good enough. And let me keep going. For D, we want f prime of 3. And what is it? 4, 5, 6, 7. Yeah, so we're just going to keep going. So at 3, 1, 2, 3, I don't know. Boy, it's hard to guesstimate these. I don't know, maybe that looks more like -1 right here. This one, it's close enough. I'm going to say -1 also. And then at 4, the derivative. So here at 4, come down here. So here it's -1. Here it looks a little less steep in the negative direction. So it looks like it's starting to flatten back out. So it's not quite going to be as big as -1 in terms of size. So I'm going to say like -3/4. And then f prime of 5 would be, let's see, 1, 2, 3, 4, 5. Is that where it flattens out? 1, 2, 3, 4, 5. No, not quite. Right about here. So it looks like it's still negative slope. It's not as steep as that one was. It's flattening out even more. So maybe I can put like -1/2. And then I believe when we get to 6 or 5, 1, 2, 3, 4, 5. Oh, wait a minute. Hold on. 1, 2, 3, 4, 5. Okay, now, yeah, we're at 6. When we go to 6 for the x value, it looks like we're at the bottom. So that's going to have a slope of 0. And then if we go f prime of 7, 7's right here. We're here now. Notice that the slope is slightly positive, just a little number, so maybe like +1/2 or +1/4, whatever. We're estimating. And now what we're going to do is we're going to use this information to graph the derivative. So if I were to look at the derivative of this function on a different graph, then at 0, the function is 10. So at 0, we go up 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up here, and we draw a dot. And then at 1, we're at 0. So at 1, we're at 0. At 2, we're at -1, which will be, let's say, about right here. Let's say that's -1. And then at 3, we're also at -1. So something like that. At 4, we're at -3/4, which would be somewhere around here. So coming up a little bit. At 5, we're at negative 1/2, so it came up a little bit more. At 6, we're at 0. And at 7, we're at 1/4, which is about right here. Now, if we connect these together, the graph looks something like this, okay? So that is the graph of the derivative. Now, let's try and analyze this a little bit better by looking at this tangent line. So our tangent line starts out really steep, 10, so it's positive, it's above the x-axis. Then as we move over here, notice the slope of the tangent line is still positive. So notice my finger is still above the x-axis here, it's still positive. Until I get to 1, then it flattens out to 0, so I pass through the x-axis here. Now I'm going to start to have negative slopes. They go down till you get to negative 1, and then it starts coming and flattening back out towards 0, and then it gets to 0. Then once I get past this point, I start pitching up again, so the slope is positive. So whether or not the point lies above or below this x-axis here corresponds to whether or not this slope of this tangent line is positive or negative. Has nothing to do with whether or not this graph is above or below the x-axis. So there's your graph of your derivative. I left number 1 for you to do. Now, on number 3, it's a matching game. So I'm just going to pick maybe 2 of these and show. So let me pick, and I think I took it. Oh no, I didn't, okay. Let me take, there's 4 of them. So let me take the first one. This is number 3, part A. Or A is this function. It's like this, comes down, comes back up, comes back down like that. And we can assume those are like arrows like that. So I'm trying to match it up with its derivative. So I'm gonna below this try and graph its derivative. And here's where I'll start. I'm gonna start at the points I know for sure, and that would be right here at this x value, which is this x value. The slope of the tangent line here is flat, so it's 0, so I know the derivative has a value of 0. Also here, the slope of the tangent line here is flat, so the slope should be 0. So when I graph at this x value on my derivative function, it should be here. And now let me just look at any other points that might be easy for me to get. How about at 0? The slope of this tangent line looks about 1. I don't know, the picture that's drawn there might be better. Maybe it's 1, maybe it's 2, I don't know. I'll just put it here. Let's just say it's about right there at 1. Okay, so I know those points for sure are on my derivative graph. And now let me look to the left of this point. If I look to the left of this over here, all my derivatives are going to be, all my tangent lines are going to be negative as I move this way. In fact, it looks like I start out as a little negative slope, so I should have a little negative number here. Then it gets a little bit steeper, so a little more negative, a little steeper, a little more negative, and it keeps on getting steeper and steeper, which means it gets more negative and more negative. So I'm just going to do something like this. Now, if I move to the right of this point, the slope of my tangent line is positive, not very steep, so a small positive number. And then it gets steeper and steeper until it gets to 1. So this is just going to go up towards 1. And then once I get past this point, notice that it still has a positive slope, and it's about 1, and then it starts to flatten out. So it's going to get closer and closer to 0, which means it's going to connect these 2 points together. But notice they're all above the x-axis, so that means the derivative is positive, and that corresponds to the slope being pointed up like that. Then once I get past this point, my derivatives start to be negative, right? Small negative numbers, and then they get steeper and steeper and steeper and steeper, so it becomes a big negative number. So it's going to go something like this. So if I were looking at these options, I'm thinking option 2 would be the best option. Let me see, I think part D is pretty clean. How about B? Let me draw B. For b, we have this kind of zigzag looking thing. That. Now those are straight lines. These are straight, 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 sharp corners here. So when I look at my derivative, I want to keep in mind that anywhere that I have a corner, my function is not differentiable, so my derivative will not exist there. So I already know that right here, right, corresponding to that x value, and right here corresponding to that x value, my derivative should not exist there. Now, if I pick a point over here, any point here, anywhere on this line segment, any of those, the slope of the tangent line is actually just the slope of this line. It never changes. So as I move along this function, that derivative is always the same, which means that, well, if it's a positive number, which it is because it's sloped up, whatever positive number it is, it just stays that way. So to the left of this, I'm some positive number. Watch what I do here. I'm some positive number, and I stay that positive number the whole way until I get to this point right here. And then all of a sudden, my derivative flips over, switches, and becomes negative, and then stays that negative value the whole time. So it's some negative value. I don't know what it is. And it stays that way all the way until I get to here. It just stays that same flat line, or not flat, straight line. And then once I get to here, it switches up immediately again to a positive and stays that same positive the whole time. So it goes back up to whatever this was, because these look like they're parallel. And it just stays that the whole way. So that looks like our derivative, which is option 4. All right, and I'll let you try and get C and D. And let me move on to number, let's see, you have 5. Yeah, let me do 5. You should try all of these, by the way. You should try 4, 5, 6, 7, 8, 9, 10, and 11 on your own just for practice. But I assigned this 5. So we go like this. Goes up. And then it comes down. And it looks like it tapers off like an asymptote here. All right, so I'm going to go and try and draw the derivative, do it below it. And I'm going to go to the point that I know for sure. This one looks like I have a slope of a tangent line of 0, so I know my derivative is 0. There. Now to the left, notice what happens. I start moving here to the left. I've got still positive slopes, but they're small slopes. So I should have small positive numbers. But as we move over more, it gets steeper, so those become big positive numbers, small positive numbers, Robert, sorry. Small positive numbers. And then as we move this way, I should get bigger and bigger positive numbers, so it should do something like this. Now, if I move to the right, I get small negative numbers, right? So I get small negative numbers, and it starts to get steeper, so it's going to get more negative. But right around here, it starts to switch back, turn the other direction, but it's still negative slopes, they're just not that big. And I keep trying to flatten out to 0, but I can't quite get there. Flatten out, I know my function is approaching 0, but the tangent lines are starting to try to flatten. So that means that the derivative is trying to get back to 0, but doesn't get there. So it looks like that. Nine looks somewhat interesting. We've got kind of like a flattened out W here. All right. I know that on my derivative, here at 0 and here, I know that my derivative shouldn't exist because I have corners. Over on this little segment, it's always the same derivative and it's negative, right? It's always a straight line, so it's always staying the same slope. So it's a negative value all the way out this way. Once I get to here, it switches to a positive value and it stays that the whole time. So it's positive until I get to here. Once I get here, it switches to a negative value, which looks like it's the same because it's parallel to this. So it switches back down to negative, goes out to here, and then once I get here, it switches back to the same positive this one was because they're parallel. So back to here and out. There's my derivative. 11 is kind of interesting. We've got something else going on in 11 that we haven't had up to this point. Yep, looks like that. All right, so let's talk about this. Let's talk about the derivative. Well, I don't have anywhere where it flattens out and I don't have any corners, but what I do have is right here at 0, it looks like the slope of the tangent line becomes vertical. So as I'm moving here, I start to try and straighten out, tries to straighten out, and we know that vertical lines don't have a slope, they're undefined. So over here, let's say right at this point, right, this x value, I have some positive slope. It's not very big, but it's some positive number. Okay, let's put it here. I'll just put it here. There we go. That's what it is. As I move over, these start getting, this is getting steeper, so it's getting bigger positive numbers. So as I move over, I'm getting bigger and bigger positive numbers. But as I try and get close to 0, that slope tries to become infinitely large. So on my derivative, it's going to have an asymptote like this. And then once I get past 0, let me start back from this end. Here I have a positive slope, right? It's not very big, so here I have a positive slope. If I start moving backwards to the left, my slope gets more positive, more positive, more positive, and then eventually again tries to become an infinite slope. So as I move to the left, I get bigger positive numbers, and it gets more, it approaches an infinite slope, so it goes like this. So that is the derivative of that function. All right. 13, I think that's something, I like to leave the word problems for you to try and figure out. Let's get to 19. Boy, 19 is pretty straightforward. All right, it's the first one, we'll do it. F of x equals 1/2 x minus 1/3. And we're asked in this problem to find the derivative of the function using the definition of the derivative, state the domain of the function and the domain of the derivative. So we want to use the definition, and the definition we're going to use is right there at the beginning of the section. So let's do it. The derivative of f is the limit as h goes to 0, f of x plus h minus f of x all over h, which means we want to take the limit as h goes to 0. Now we're going to plug x plus h into this function. So 1/2 times x plus h minus 1/3. That's plugging x plus h in here. Minus, now we want to plug x into there. Well, that's just that. So I want to subtract, and be careful, parentheses, the whole thing. All over h, limit, h goes to 0, distribute, 1/2 x plus 1/2 h minus 1/3 minus 1/2 x plus 1/3 all over h. 1/2 x cancels, 1/3s cancel. you're left with 1/2 h over h. The h's reduce out, and all you're left with is 1/2. So you have a constant. That's all that's left. And the limit of a constant is the constant, so you get 1/2. And this makes sense because this is a line. And since you have a line, the slope of the tangent line should be the same as the slope of the line, and the slope of the line is 1/2. So it makes sense that that would be our answer. We have the same slope regardless. Now let's look at 20. By the way, the domain of that function was everything, and the domain of the derivative is everything. Because it was a polynomial, it was well behaved. You don't have any issues. We'll have some issues later on as the functions become more complicated. I think maybe, I think that you can handle 20 and 21, all right? Because I did enough of those in the past, different versions, that I'm pretty sure you can get those. Let me get to the more interesting stuff like 22. G of t equals 1 over root t. First, let me talk about the domain. The domain of G is that t must be an element of the interval 0, infinity. In other words, t must be bigger than 0, and of course less than infinity. Because you have a root, right? You can't plug any negative numbers in, and you can't plug 0 in here because then you would have division by 0. So we've got to just have t's be positive numbers. You could also write t is greater than 0. All right, so that's the domain. Now, let's get the derivative. G prime of t equals limit h goes to 0 of g of t plus h minus g of t all over h. So notice, instead of f prime of x, we have g prime of t. So the f's being replaced with g's, and the x's are being replaced with t's, and so we get that formula. So this is limit h goes to 0 of, let's plug this in, 1 over square root t plus h minus 1 over square root t all over h, which is the limit as h goes to 0. Now, we have a complex fraction, we have radicals. I'm first going to get a common denominator, I'm going to put these two together. So to do that, I have to introduce root t plus h here, root t plus h here, introduce root t. We've done this before. Put the numerators together, you should get root t minus root t plus h over the common denominator, which is root t times root t plus h. I'm not going to put those together. All of this over h. And we still have a problem if we let h go to 0. I don't know why I put 4. Probably because it's Friday. And if we try and let h go to 0, we're going to get 0 over 0 still. So here's where we come in with the conjugate. So I'm going to multiply the top and bottom here, root t minus root t plus h over root t plus. Man, my brain is not wanting to work today. Multiply here, and then on the bottom that's going to be real ugly. I'm not even going to touch it. So let's see where we are. This equals the limit as h goes to 0. Now, when I do this, I'm going to get a t minus, right, because minus and plus, the middle terms are gone, whatever was underneath that root, so t plus h. Then over, look at this nasty thing, root t times root t plus h times, in parentheses, root t plus root t plus h. All of this over h. And good things are about to happen. When I distribute the negative through here, I get negative t minus h. This t and this t cancel, I'm left with negative h. Then I can rewrite this as h over 1. I can flip it up as 1 over h here. There's a lot going on right now. Flip that up. This is gone. Don't need this division bar. And now this h and this h cancel. And all we're left with is negative 1 on top. So once you do all this cancellation, this will just be negative 1. Just saving myself some time by erasing. And now I let h go to 0. So if h goes to 0, that goes away, and that goes away, and I'm left with no more limit, negative 1 over root t times root t again, times, in parentheses, root t plus root t. So root t times root t is just t, and then root t plus root t is 2 root t. And so we have negative 1 over 2t root t. And you can look at the t root t as being t to the first power times t to the half power. And if you add the exponents, you get 3/2 power. So you could also put negative 1 over 2t to the 3/2. Both of these are good answers. You could even, if you want, although this would be very unnatural for you to want to do this at this point, you could write this as 1/2 t to the negative 3/2. Because you could bring this up, and that would make it a negative exponent, and then you could rewrite the negative 1 over 2 as a negative 1/2. I'm going to box this because we will see that later. All right. Let's move on to number 23. G of x equals root 9 minus x. Oh, I didn't talk about the domain. I apologize. I should have talked about the domain of this. We had negative 1 over 2 root, t root t. It's the same domain. T has to be bigger than 0, or else we'll get the root. We have to worry about negatives, and then we can't have 0 on the bottom because we'll have division by 0. So t must be greater than 0 for the domain of the derivative. All right. The derivative of g is limit h goes to 0 of g of x plus h minus g of x all over h, which is the limit as h goes to 0 of square root of 9 minus x plus h. Be very careful when you plug x plus h in here, right there. The minus is in front, so it's going to distribute. And then 9 minus x here under the root, and then h. And I think you can see pretty much straight away, hopefully, that we're just going to come right in with the conjugate on this. Multiply this by root 9 minus x plus h plus root 9 minus x. And then we're going to do the same thing on the bottom. Root 9 minus quantity x plus h plus root 9 minus x. And when we do the top multiplication, the middle parts go away, so it's just this root and this root, which means everything goes away, or the roots go away. And then the last one will have a minus, and then whatever was under the root. So in parentheses, 9 minus x. And then we have this ugly denominator, which had the h in it, and then this parenthesis, and then all this. Root 9 minus x plus h, and then plus root 9 minus x. And let's see, we should get some nice cancellation up top. I'll write this again, limit h goes to 0. Let's see, 9 minus x minus h minus 9 plus x over h parenthesis root 9 minus the quantity x plus h plus root 9 minus x. The 9's are gone, the x's are gone. You get negative h on top, h on the bottom. These cancel, you're left with the negative 1 on top. So let's do negative 1 over, we're going to take the limit now, negative 1 over, let's let all our h's go to 0. So if this h is 0, this is just x, 9 minus x root, okay, plus 9 minus x root. So we have two exact copies of each other. So this is just going to be 2 of the square roots of 9 minus x, right there. All right, let's talk about domain here. On the domain, the original function g, notice that the domain is that we just can't have a negative under here. So 9 minus x must be greater than 0, which means that 9 must be greater than x. Strictly greater, so on a number line, 9, x must be smaller than that, so it's everything over here. Oh, I'm sorry, greater than or equal to. We can have 0. 0, square root of 0 is fine. 0, so it's everything over there. That's the domain of g. But if we look at the derivative, because this root appears in the denominator, this can't be 0. So the domain of this is the same as that, except we don't have the equality. You just have the strict inequality that x must be less than 9. Okay, that's it for that. Okay, I have a meeting in 15 minutes. I'm going to do one more problem. I'm going to do 24. 24 looks pretty nasty. F of x is x squared minus 1 over 2x minus 3. All right, let's do it. The derivative of f is the limit as h goes to 0 of f of x plus h. So I plug x plus h into this. X plus h squared minus 1 over, oh, ugly, 2 times x plus h minus 3. So I replace that with x plus h, that with x plus h. Now minus f of x, which is x squared minus 1 over 2x minus 3, then all of this over h. Now I'm going to give myself a little more room because I'm going to need to do a common denominator. I'm taking the limit as h goes to 0 of this. All right, well, common denominator. I need this and this to appear. So let me do this one over here. I'll do 2x minus 3 here. 2x minus 3 here. Over here, this is going to be really ugly. This is going to be 2 times x plus h minus 3 over 2 times x plus h minus 3, top and bottom. And I'll be distributing through. It's going to be nasty. All right. Here it is. I have the limit as h goes to 0. This times this, let me write that down, 2x minus 3 times this thing. Now, I'm going to need to expand that out, I think. So let me, well, should we? I don't know if we should. I guess we will. Let's expand that. X plus h squared, you go do that on your own, blah, 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 blah. We'll get x squared plus 2x plus h plus h squared, then we still have minus 1. And then over here we have minus, because we're putting these two numerators together, x squared minus 1 times this thing, I'm going to distribute the 2 through, 2x plus 2h minus 3. All of this over this really ugly denominator, 2x minus 3 times 2 times x plus h minus 3. That's the common denominator. Then that whole expression, the whole thing over h. Now that looks really bad, huh? This equals the limit as h goes to 0. Now what I'm going to do is multiply this times this. So I'm going to do a 2x through to each of those, like that. Let me do that first. So 2x times x squared is 2x cubed. 2x times 2xh is 4x squared h, and it's positive. 2x times h squared is going to be 2xh squared. And 2x times -1, negative 2x. So that's the 2x pass through. Now the -3 has to pass through. So -3 times x squared is -3x squared. -3 times 2xh is -6xh. -3 times h squared is -3h squared. And -3 times -1 is positive 3. Okay, that's just that one. Then I have minus whatever this turns out to be. So I have to figure out what all of this is and then subtract it. So I'm going to go here to here first, which is going to be 2x cubed, but I'm going to subtract it. So minus 2x cubed. Then I'm going to do here to here, which is going to be x squared times 2h, which is 2x squared h, but then I'm going to subtract it. So minus 2x squared h. Then I'm going to go here to here, which is x squared times -3, which is -3x squared, but then negative, so positive 3x squared. And then -1 times 2x is -2x, but I'm subtracting, so positive 2x. And then -1 times 2h is -2h, but I'm subtracting, so positive 2h. And finally, sorry about that, -1 times -1, or sorry, -1 times -3 is 3, but then I'm subtracting, so minus 3. Wow. Is that not a big numerator or what? And then over the denominator, which was 2x minus 3 times 2 times the quantity x plus h minus 3, then all of this over h. Now, I'm hoping for some cancellation here. I'm counting on it. 2x cubed, this better go away because it doesn't have an h in it. And I need nothing but h's left up here, so this is gone. Okay, this one might still be here. Let's see the things that don't have h's. Minus 2x plus 2x. Let's see, minus 3x squared plus 3x squared. That has an h in it. 3 minus 3. Okay, so everything that didn't have an h does cancel. Now let me see if I have any like terms. Here I have a term that has x squared h in it. And I have another one down here that has x squared h in it. So let me put those together. Limit, h goes to 0. 4x squared h minus 2x squared h is just 2x squared h. And then xh squared, I don't see another xh squared. So just plus 2xh squared. So I've done that, I've done that, I've done that. Let's see here. Minus 6xh, I don't see any other xh's, so minus 6xh. Minus 3h squared, I don't see any other h squareds in it, so minus 3h squared. And plus 2h. All over my common denominator, 2x minus 3, 2 times x plus h minus 3, then all of this over h. Factor an h out of the numerator. I'm going to go ahead and factor an h out right now. I'm going to do a shortcut here. I'm going to pull an h out. which makes that h go away, makes this h squared become h, makes that h go away, makes that h squared become h, and makes that h go away completely, like that. So I pulled that h out and it cancels. You could also do h over 1 and flip it and cancel, it's the same thing. And now at this point, I can let h go to 0. And let me see what happens. H goes to 0. We get, this is 2x squared, there's no h here. So it just stays there. This goes away completely. This goes away completely. And so we're left with 2x squared minus 6x plus 2. 2x squared minus 6x plus 2 over 2x minus 3 doesn't change. This h goes to 0, which means this is just x. So this is 2x minus 3. So we have 2x minus 3 times 2x minus 3 squared. I believe you can factor out a 2 on top, but it's not necessary unless that would somehow help me factor the top, but the top does not factor anymore. So this is it right here. All right, I've got to take a break for a meeting. Working number 26. By the way, on the previous problem, I didn't talk about the domain of f on number 24. 2x minus 3 cannot be 0. So 2x cannot be 3. So x can't be 3 halves. And it turns out if you look at the derivative, it was the same domain. So everything except that number, which you could do in interval notation, or you could just write that. All right, so this one, here's our function. We're trying to find the derivative. So we're going to do the limit as h goes to 0 of f of x plus h. So plug into this x plus h raised to the 3 halves minus f of x, which is just x to the 3 halves, over h. All right, now we're going to run into a little bit of an issue here because algebraically we haven't really messed with anything like this yet. So maybe we look at this slightly different. Just remember that if you have, let's say, x to the 3 halves, that this is the same as the square root of x cubed, but that's the same as x cubed square root. So these are all the same. I'm going to look at this one right here, rewriting those in that form, just because I'll have some radicals, and then maybe I can come in here with that conjugate idea. So this is square root of x plus h cubed minus square root of x cubed all over h. And now let me just see what happens if I hit this thing with the conjugate. So I'm going to come in here, multiply by square root x plus h cubed plus square root x cubed, and do the same thing on the bottom. Square root x plus h cubed plus square root x cubed, like that. And when I go and do the numerator, here to here, all I'm left with is what was under the root, which was the x plus h cubed. And then the middle terms are gone, and then the last terms I get a minus, and then what was under the root, which is just x cubed. Ooh, that's nice. Nicer. The denominator is this h times all of this, and I'm not going to even attempt to mess with it. Like that. And then I'll do another line where I'm going to expand this out. When I expand that, I get x cubed plus 3x squared h plus 3xh squared plus h cubed. Then I still have that minus x cubed all over h, and then square root x plus h cubed plus square root of x cubed. My x cubes cancel. Everything left has an h in it, so let me just cancel out an h. This h goes away, right? This h squared becomes h. This h cubed becomes h squared. And then that h canceled out with the h that I pulled out of the top. And this is all I've got left, okay? So I'm going to erase these just so I can save myself having to write another line. I have this. That's where I am. Now I can let h go to 0. So that goes away, that goes away. I get 3x squared on top and on the bottom. If this is 0, this is just x and x cubed and then square root. So I have square root of x cubed plus, again, another square root of x cubed. That's 2 of them. So 3x squared over 2 square roots of x cubed. And now I'm going to mess with this a little bit. I'm going to say that that's 3x squared over 2x to the 3 halves, because that's what that meant. And now I'm going to use properties of exponents. X to a power divided by x to another power, you subtract. So we'll get that that's equal to 3 over 2. And then I'm going to be doing x to the 2 minus 3 halves, which is going to be 3 halves x to the 1 half, which is 3 root x, because x to the 1 half is the square root of x, over 2. There we go. And that's it. Interesting. I'll let you do 27. I think that's doable. All right, so looking at number 33, I don't see any higher derivatives. Where are they? I also don't see any velocity problems. I'll have to do those in class. So 33 gives you a graph. And it looks like this. We've got here, solid dot, jumps up, and then you got something like this. Yeah. Something like that. It says here, the graph of f is given state with reasons, the numbers at which f is not differentiable. So right here, whatever x value this is, which it looks like 1, 2, 3, 4, -4, we have a corner. So at x equals -4, we have a corner. So it's not differentiable. At 0, we have a jump. It's not continuous. So it's not differentiable. And at, well, it looks like maybe, I don't know, it's tough to say. I'm not sure if they want you to do this, but we're, at this point right here, it looks like we may have a vertical tangent line. So it's hard to say if they really want that. I'm going to say that happens at like 2.5. 2.5, we have a vertical tangent. So those would be the places where our derivative, or where our function is not differentiable. All right, that's it. I believe that should be enough to get you through this assignment. Like I said a minute ago, there's going to be some stuff I do in class in this section that will fill in some of the other gaps that I did not do in the homework set. So in other words, make sure when you review for a test that you're looking at both the lecture video and this homework video.